Hello, today we will continue to learn transfer function from chapter 2, and we will see the electromechanical system where we have an electrical input EA, but we will have a mechanical output, for example xt, or mechanical output, it can be rotational, which is theta. So in this case we will have a combination of electrical and mechanical input output. So let's see. So we will start with writing equations for DC motor, because most of our electromechanical system consists of a motor. So when considering the motor, we have already learned this type of circuit for DC motor system, where we have a electrical input to the armature of the motor, and there is a armature resistance, inductance, and when the rotor moves proportional to the speed of the rotor, there is a back EMF VB. So here in this circuit we get EA, R, voltage drop in RA and LA, and there is a back EMF VB, and the rotor is connected to external mechanical system, where we will develop a torque. There will be a torque developed, and there will be some rotational displacement theta m, etc. Okay, and with this axis of the rotor there will be some inertia, some viscous damper, and some constant, some spring as well. So our target is to find a transfer function where the angle theta m is the output and electrical input EA is the input. Okay, so this is electrical input, mechanical output, and we are interested in finding out GS. So let's see. So to begin, we will start writing KVL equation in this circuit. We can see that we can easily write these equations. There are three different voltage drop: I, RA, IA, LA, IA, and VB. But in this case we already know the impedance of LA is LAS into current IA. So this is the basic equation, but in this equation we have the electrical input, but we do not still have the mechanical output, which is theta m. So we need to convert all of these terms to theta m. Okay, so somehow we need to write these terms in terms of theta m. So how can we write this? At first we have to remember from our previous knowledge that our back EMF is proportional to the speed of the rotor, and the speed is nothing but d theta m by dt, which is omega m, right? So this term is omega, which is the speed, and Vv is proportional to it, and this is the constant Kv, and we call it back EMF constant. So in Laplace domain, if we take Laplace, we get Vvs is equal to Kb into S. There is a S into theta m, right? So we are going to use this in these equations. So we will replace Vvs with this. Okay. Secondly, we have to remember that our developed torque in the rotor is proportional to the input current in the armature. So the more the current, the more torque we will have, right? So, and the equation is like that, is like this: Tm is equal to Kt into Ia. So this is a constant here, Kt. So and we will also use our previous knowledge on mechanical system, that is Tm is equal to theta m into some impedance, right? Here we have written some inertia jm square s square plus dm, which is viscous damper, into s. So this gm or dm are connected to this rotor. Okay, so whatever inertia is connected with this axis of rotor, we'll write it as Jm, and whatever damper or friction is connected to this rotor, we will write it as Dm, right? So now let's use all of these formulas in the equation. At first, replace the Ia. We can take the Ia and replace it with Tm divided by Kt, right, from here. So we replace it with Tm divided by Kt, and in this case we can actually neglect this La, which is much less compared to Ra, so we can actually neglect this. Anyway, we can rewrite this equation by replacing Tm with this term, that is theta m into jms square plus dms. Okay, so this is from our previous lecture. In writing rotational system, we can always write a relation into like this: theta m into some impedance is equal to applied torque, etc., right? So we have used it to replace the Tm. So finally what we get is we have the input on the right side and we have the output on the left side. Okay, so now all the variables are replaced with theta m. Now we can easily write the transfer function. Here, in writing the transfer function, we neglect the La. We consider La is negligible. So if we consider that, we can rewrite this equation in this format: theta m divided by Ea, something like this. And in simple, this transfer function is a second order transfer function, which is a constant in the numerator, and this is something like s into s plus alpha. The value of alpha you can see here, right? So in our next section, we are going to use this transfer function directly. If our system looks like exactly this one, we can use this transfer function directly. Okay, but we will see later that some of our system will not be look like this one, and there will be some additional spring, additional viscous damper, which is in cascade format. So in that case, there will be more than one independent variable. We can see that here the rotational displacement is just one, theta m, but we will later see that there can be more than one independent variable. So in the case of more than one independent variable, we will need another equation which can be written from this equation. We will rewrite this equation by assuming L is negligible in this format, which is TMS is equal to Kt by Ra into Ea minus this term, which is this one, right? So we will also use this formula in solving a system where we have more than one independent variable. So if the system consists only one variable, we will use this. If the system consists more than one variable, we will use this equation. Okay, so in the case where there is a two variable, for example, we cannot write these equations. This equation is no longer true if there are more than one independent variable. Okay, we have to solve it in another way, and in that case this formula will be very helpful. Anyway, let's move on. So Now let's say a motor system where there is a gear, okay, and through gear some additional inertia and some additional viscous damper is connected. So in that case we have to find some equivalent parameters, and after finding those parameters we have to replace the dm, we have to replace the jm here, etc. So let's see one by one. At first we will find the jm. Here we can see that there are two inertia, one is associated with the rotor itself and another is associated with the right side of the gear, which can be considered as load. So there is a two part, one is part of motor and another is part of load. So we are going to combine these two JL and JA together to find the equivalent JM which is used here, okay, in the original equations. So in our, when we were deriving this equation, we just assumed that there is the equivalent inertia is Jm and equivalent inertia is viscous damper is Dm, right? So now we are going to find this equivalence from these two combinations. So we already know how to find the equivalence for a gear based system. So we are finding the equivalence on the left side of the gear because the motor is connected to the left side. So Jm will be equal to Ja plus the transfer version of Jl, which is Jl into N1 by N2 whole square. Similarly, we can find Gm. So we will use these two formula to find the equivalent Jm and Gm, which will be used in our original transfer function. Okay. Now we have two more parameter. One is Kt by Ra. We can see that Kt by Ra is here and here as well, and another parameter is Kb, and we are going to find these two parameters. Let's see. So to find that, remember there is an equation in our previous slide. So we are going to use it. We are going to rewrite this equation in time domain, where we can replace s into theta m with omega m, because we know s into theta m is nothing but d theta by dt, right? So this can be written as omega, which is speed of the motor. Okay. So if we replace this with theta and omega and we rewrite this equation in time domain, we will get something like this. Okay. So this was in frequency domain, this is now in time domain. Now if we rewrite this equation in this format, we will see Tm is equal to something into omega m plus something, which is like a straight line, y equal to mx plus b, right? Mx plus c. So this is a, if we consider Tm and omega m are our variable, then this is a straight line. Okay. So we will see that the curve Tm and omega m is following something like a straight line, where if we increase the omega m, we will have a decreased torque, and vice versa. If we, that means if Tm is the developed torque here and omega m is the developed speed here, the relation, all the possible combination of Tm and omega m will stay on a line like this. The motor speed and torque will be somewhere in the line. It will not be here, or it will not be here for a given input voltage. For a given input voltage, the combination of torque and speed will be on this straight line. So now this graph is going to help us in finding Kt by Ra and Kb. Okay. So how is that? I think all of us have done an experiment on this in your energy conversion lab. When we set the omega equal to 0, that means we are here. So according to this characteristic line, we will have a torque equal to, which is called stall torque. Okay, if we decrease the omega m to 0, which can be just achieved by holding the rotor by our hand and stopping the rotor, and we will feel a torque in our hand, and that torque is stall torque. Okay, so when we somehow stop the rotor, the omega m is 0, and whatever torque develop in the rotor, in that case is the stall torque, and that is the maximum torque can be developed in the rotor. So in the maximum torque is stall torque, and we will put this stall torque in this equation. Tm is equal to T stall, and we also put omega m is equal to 0. In that case, we will get the equation for Kt by Ra, which will be equal to T stall is equal to Kt by Ra into Ea, and thereby we can find Kt by Ra is equal to T stall divided by Ea. So what we need to find Kt by Ra is the value of this stall torque and the value of input voltage to the motor. Okay, and similarly, if we make the torque 0 by, for example, letting the rotor to rotate freely, we will have 0 torque, and in that case we will get maximum speed, which is called omega no load. Okay, so in this point, when we let the rotor rotate freely, right, so in that case the torque will be 0. Okay, torque will be 0, and the speed will be omega no load, and according to this equation we will get omega no load is equal to Ea by Kb. You can see if we put 0 here, okay, we will get something like this, and where we can cancel this Kt by Ra term, and we will get these equations, that is Kb into omega no load is equal to Ea. So from that equation we will get Kb is equal to Ea divided by omega no load. So to find Kb, what we need is omega no load. Okay, the speed when there is no load connected to the rotor. So by using these two equations, we can find these two parameters for to solve our transfer function. Now if we solve all these 4 parameters, we can rewrite the transfer function. Okay, so you have to remember these 4 equations, and you can also see for different input voltage we will get actually different lines actually. So it will be given in our question, okay, what is the input of the motor. So let's solve an example 2.23, where we have a motor system. We have given some inertia and viscous damper constant for the rotor, and by connecting we also have extra load, inertia and viscous damper, which is connected to the motor by a gear. Okay, and we are also given some characteristic of the motor. Now what we need to do is to find the transfer function, right? So to find the transfer function, what we need to find is dm, jm, Kt by Ra and Kb. Okay, so let's find one by one. At first, jm, we can find easily the jm by combining this pipe Ja with this 700 but given we must transfer this inertia to the left side by this ratio, that is 100 by 1000, which is this one, 1 by 10 whole square. So by converting this inertia and by combining with the left side, we can find equivalent Jm. Similarly, you can find Dm. Okay, similarly. So now we have to find Kb and Kt by Ra. Okay, so let's find it. So for that we need the characteristic from this curve. We have TS12 500, we have omega no load 50, and we have input voltage 100. Okay, so we are going to use them to find Kt by Ra using the previous formula, and we will also find Kb, and we are going to use all these 4 values in our transfer function to find the transfer function. But sometimes we will be required to find transfer function like theta L by theta Ea. Okay, so in that case we can see that theta m is just on the motor side and theta L is on the load side. Sometimes the question will mention that this is the output, so I have to convert this theta m into theta L by using this 2 ratio, n1 by n2. Okay, so we have to use n1 by n2, this ratio, to convert theta m into theta 2, and we can easily convert it. We know the equation, that is theta m by theta L is equal to n2 by n1, which is 10, and from there we can find something like this. Okay, we can write the theta m, replace theta m with 10 theta L, and finally we rewrite the equation something like this, etc. So that's all. I think this is pretty straightforward. Let's go for next example. Please try to solve some example by yourself. Here we have given another similar example, but just gear ratio is we have a new gear ratio which is 20 by 100 into 25 by 100. Okay, so we have to multiply these 2 ratio together to get the equivalent gear. Okay, and also instead of giving a characteristic curve, we have given some characteristic equations. So I think you can also easily solve this equation if you compare this equation with our derived equation in our previous slide. If you compare this, we can easily find Kt by Ra from this equation. So I hope you will pause this video here and you will solve the transfer function, which should be this one. Okay, after you finish this example, you can try to solve more challenging example, something like this. Don't worry if you cannot solve this by yourself. I will discuss in our next live session. So here, for example, we have this is something, a combination of rotational and translational. You can see there is a rotational part and there is a translational part, and the gear is named as ideal gear 1:1. That means 1:1 means there are some teeth here and there are some teeth here, which is translational. This will move just up and down and this will rotate, right? So if we move one gear in the rotational system, there will be one gear movement in the translational system. So this is called 1:1. Anyway, to solve this system, we need to go back to the geometry where we can find x equal to r theta. R is the radius here, x is the this movement, theta is the angular movement here. Okay, x equal to r theta. So you have to write that equation to solve this kind of problem. So I will not discuss much today here, and we will see more example here where the motor is combined with the translational and rotational combination of the mechanical system. So this is more complicated things, and if you compare this figure with this figure, actually between these two example, this is relatively easier, because if you carefully note that the number of variables here will be 3 and number of variables is just 1 in this case, even though it looks very complicated, but in this example the number of variable is just 1. I will explain it later. Okay, so try to solve this if you can. We will discuss it later.